Hello there! In this video you will learn about the basics of electric current. You have surely seen the indication of an electric current on your charger cable, as for example here on my charger cable, an input current of 0.5 ampere. Let's try to understand what this value physically means. In our universe, there are electrically charged particles that interact with each other. Some are positive, others are negatively electrically charged. Electrons and protons, of which atoms are made up, are for example such electrically charged particles. Electrons are negatively charged, protons are positively charged. When you bring two positively charged particles closely together, they repel each other. Two negatively charged particles also repel each other. When you bring a positive and a negative particle together, they attract each other. Through such repulsion and attraction, charged particles interact with each other. Experiments have also shown that these charged particles do not all attract or repel each other equally strongly. There are charged particles that attract each other more than others. To quantify this difference in attraction and repulsion, we say that charged particles carry different charges Q. The charge is measured in the unit coulomb and is abbreviated with the letter C. The greater the charge Q of a charged particle, the more it's repelled or attracted by other electrically charged particles. In order to distinguish positive and negative particles, we assign a negative sign to negatively charged particles. For example, Q is equal to -1 coulomb, -2 coulomb, -3 coulomb, and positively charged particles we assign a positive sign. For example, Q is equal +1 coulomb, +2 coulomb, +3 coulomb, whereby we can of course leave out the plus. But what do electric charges have to do with electric current? Let's do a little thought experiment with what we know so far. Take two boxes with a hole that can be opened and closed. First we close both holes. In one box we put many positive particles. Each of them carries the same charge Q, and for fun it is 1 coulomb. In the other box we place many negative particles, each with a negative charge. The two boxes now form a large electric charge. We can also say that the negative box forms a negative pole and the positive box a positive pole. The two charged boxes will now of course attract each other. To prevent this, we fix the two boxes so that they cannot move towards each other. Next, we connect the two boxes with a conductive wire, for example a copper wire. By conductive we mean that charges can move through this wire. What happens to the positive charges in the positive box when we open it? The positive charges can now move to the negative box along the wire. Why are they doing this? Well, because they are attracted by the negative charges. This movement of the charges is an electric current and it's in the direction of the negative pole. Qualitatively speaking, the current becomes larger when more charges pass through the wire. But how do we quantify the current now? Let's abbreviate the electric current through the wire with the letter I. Then we concentrate on a cross-sectional area of the wire. If we cut the wire, we would get such a round circular area here. This circular area is called the cross-sectional area of the wire. The positive particles will of course pass through this area. Let's count how many particles pass through it. Let's do it for 10 seconds. We use the letter N for the number of charged particles that have passed through the area. Here we go. One particle has passed, second particle has passed, third, fourth, fifth, stop. 10 seconds have already passed. So we counted 5 particles. How much electric charge was now transported through the cross-sectional area? Let's label the total charge with a capital Q. If 5 charged particles passed through and each of them transported the charge of 1 coulomb, then in total 5 coulomb were transported. We just multiply the number of particles n with their charge q. So 5 coulomb of charge were transported through the cross-sectional area within 10 seconds. To find out the current I, we should answer the question, how much charge per time has passed through the cross-sectional area? Well, there were 5 coulomb per 10 seconds, so capital Q divided by T. That's 0.5 coulomb per second. So 0.5 coulomb of charge is transported through this cross-sectional area every second. The unit coulomb per second is abbreviated to A. A stands for ampere. In our thought experiment, we assigned a random value of 1 coulomb to the positive particles. But in reality, the particles carry a much smaller charge. Usually, the negative electrons are responsible for the electric current in conducting wires. They carry a tiny negative charge, namely minus 0.000000000000000000016 coulomb. For the electrons to generate a current of 0.5 ampere, 3,125 quadrillion of electrons per second must pass through the cross-sectional area of the wire. This number is unimaginably large. For the 0.5 ampere, which at first glance appear to be minuscule, an unimaginable number of electrons must pass through the wire. So to sum up, the electric current I is charge Q per time t. The current therefore tells us how much charge per second is transported through a cross-sectional area. In order for the current to be generated at all, charged particle must be set into directional motion. This directional motion occurs when positively and negatively charged particles are separated and then attract each other. The separation of charges is characterized by the so-called electric voltage. But this is a topic for another video. With this in mind, bye and see you next time.